The Great Pyramid of Giza has stood in the Egyptian desert for over 4,600 years, an architectural outlier that remains structurally intact. Over those millennia, tectonic shifts beneath this region have triggered numerous devastating earthquakes. While these seismic forces frequently reduce modern steel and concrete buildings to rubble, the Great Pyramid shows no severe damage. A mountain of unreinforced stone should fracture under this level of stress, yet the structure continues to defy standard expectations of seismic failure. Heavy masonry buildings are vulnerable to a physics phenomenon known as resonance. Every physical object has a natural frequency. When the rhythmic shaking of the ground matches the natural frequency of a building, the energy is exponentially amplified until the materials shatter. To investigate Giza's resistance, researchers installed a network of 37 vibration sensors to record the monument's behavior in total silence. The data redefined how we view the structure. The readings show the pyramid reacting to movement as a dynamic vibration filtering machine. This line graph shows the environmental baseline recorded by the sensors. The Giza Plateau vibrates naturally at a slow frequency of roughly 0.6 Hz. The internal data shows a distinct contrast. The pyramid vibrates at a much higher rate, between 2.0 and 2.6 Hz. This frequency mismatch prevents the building from syncing with the earth beneath, effectively blocking destructive resonance. This 2 Hz offset creates an invisible barrier that stops the monument from shaking itself apart. Specific architectural choices generate this unparalleled protection. Symmetrical geometry, immense mass, and a solid limestone foundation provide the initial stability. Deep inside the structure, a series of stacked open voids known as relieving chambers sit directly above the king's chamber. While these chambers were originally designed to distribute the physical weight of the stone, they serve a vital secondary function. These voids act as acoustic dampeners. As seismic energy travels upward from the bedrock, the open spaces break up the waves, dispersing their power before they can reach the peak. The precise combination of a rigid exterior and a dampening interior makes the Great Pyramid a highly tuned, earthquake-proof structure. This structural stability was a development centuries in the making. Older Egyptian monuments show a clear trail of structural experimentation and architectural trial and error. Each of these earlier pyramids, such as the Bent Pyramid, possesses its own unique vibratory signature based on its specific angle and internal layout. The Great Pyramid at Giza is the culmination of this empirical process, a final prototype refined through generations of observation. Researchers are now deploying the same 37-sensor methodology across other archaeological sites in Egypt. Mapping the unique vibrations of older ruins allows scientists to accurately assess their vulnerability to future earthquakes. Modern structural engineers are currently analyzing the dampening mechanics found in the relieving chambers for use in new construction. These ancient empirical principles are now being translated into contemporary designs, helping to build a more resilient generation of earthquake-resistant architecture.